the motion of an object is modeled by a cubic function x of t equals 1/4 t cubed minus 3t squared plus 9t plus 2. We want to graph the function x of t and find and graph its velocity function and acceleration function too. All right, so in motion problems, these are kind of unusual in the sense that the x is actually your vertical variable and the t is going to be the horizontal. Okay, so I'm going to put t here and x actually goes there. Now, in order to graph the original function, we could just use the technique of making a table where we arbitrarily pick some times t and then calculate the positions for those times. Now, we can pick any times that we want. You might try something like 0, 1, 2, 3, 4. Let's see how those turn out. So when you're doing 0, you just want to plug into the formula. The formula that I'm using, of course, comes from what's given here. But I just rewrote it, leaving open parentheses so that I could plug the inputs in. And, I just want to do that for all these other iterations as well. All right, our first output is 2. Then 8.25. Okay, so these can be put into coordinate pairs that we can plot. I mean that the t of 0 would be paired together with an x of 2 to make the coordinate pair 0, 2. And then we'll have 1 paired with 8.25. We'll have 2 paired with 10. And so on. 4 goes with 6. Let's plot this one. That's going to be the vertical intercept. Then we're going to have 1, 8.25, 2, 10, 3, 8.75, 4, 6. And then I'll just do a couple more here. Like, let's try an input of 6. I get 6 goes with 2. And let's try an input of 8. Eight goes with 10. Okay. Let me try 5 as well. 5 goes with 3.25. And let's see what 7 goes with. 3.75. But we can clearly see the trend now. And we know it's cubic, so I'll try to now connect the points into a smooth curve as best I can. Okay. That is x of t. Now, could we do this maybe faster on the calculator? There's this option to do y equals and plug in a formula such as 1/4 x to the power of 3, and then do minus 3x squared plus 9x plus 2. Type in the formula that they gave. Then you can hit graph to see a graph of it. And then you can also hit second table which gives you the outputs for various x inputs like very quickly. So that would be just a super fast way of getting this thing graphed. If we had access to an app such as Desmos.com, we can do it very quickly here just by typing in the formula. But with Desmos, you can't type in x of t because Desmos just assumes that x is the horizontal. See, if you do x, it's not giving you the right graph because it's assuming that x is the horizontal variable. So if you just change it to y, then you'll get the correct graph that you're looking for. But anyway, okay, so that is graphed. Now what we have to do is we have to find the velocity function and the acceleration function. I'm going to take the first derivative of the position versus time graph, because the first derivative of the position graph will be what is called the velocity. So first derivative of position versus time with respect to time gives us the velocity versus time. That's often written like this, that the instantaneous velocity is going to be the first derivative of the position function with respect to time. All right, so our velocity is going to be the derivative of the function 1/4 t cubed minus 3t squared plus 9t plus 2. All right, now I'm going to take a derivative of each of these terms separately using the power rule for differentiation. So power rule for differentiation says that if we have a variable such as t being raised to a power, and you want to take a derivative of that, then what we do is we move the exponent down in front, making this n times t raised to the power of n minus 1. So, for example, if we had t squared and we were doing its derivative, it would become 2t to the 2 minus 1, which is just 2t. If we had t cubed and we're taking the derivative, that would become 3t to the 3 minus 1, which is 3t squared. And if we had t to the 4th and taking a derivative, it would be 4t to the 4 minus 1, which is 4t cubed. That's the kind of rule that we want to use here. Now there's another rule that's going to be relevant here, and that is the idea of taking a derivative of any constant k times a function. If we're having a constant times a function and you want to take a first derivative of this, the function f could be a function of t. Let's say that the function f here is a function of time, but k is just some constant. What we can do is actually bring the k outside of the differentiation, so it just sort of hangs out there and doesn't participate in the differentiation that we're doing here on the function, but we'll reintroduce it later and just multiply our derivative by that constant k. All right, for example, if I was taking a derivative of, let's say, 3t squared, the 3 would be allowed to come out front. And now I would just take a derivative of t squared and just bring the 3 along for the ride here. And the derivative of t squared, as we showed above, the derivative of t squared is just 2t. So you turn that t squared into a 2t. But the 3 still hangs out there and has to be multiplied back in at the end, making the final answer 6t. So let's use those rules here. I'll take the 1/4 and let it stay. And then what I'm going to do is I'm going to do the derivative of t cubed. And then just multiply the 1/4 times whatever the derivative of t cubed is. So the derivative of t cubed would be 3t squared. Okay, so that takes care of that term. Now I have to do the next term. So the -3 can be brought down. And now I need to do the derivative of t squared. So the derivative of t squared, as I showed earlier, is 2t. Okay, now I'll bring the 9 down and do the derivative of just t. That's just 1. And the derivative of a constant is 0. So this is our first derivative. We can make this then 3/4 t squared minus 6t plus 9. Now we want to plot this. It's a parabola. You could do a whole new table. That's always an option. You can pick some arbitrary times and then plug it into the velocity function. But there's certain facts that we know just from looking at this graph. I guess just to be totally rigorous, I don't want to make an assumption, but my guess is that this is going to be a local max for this position graph, and this looks like it'll be a local min. So in all likelihood, if I do plug into the velocity function, if I plug in a t of 2, I'll bet that the velocity is going to be 0 at that time, because wherever we have a max, that's a stationary point. That's a place where the tangent line has a slope of 0. And so that's going to be a place where the derivative of x at 2 is going to be 0. Also here at this local min, that's another place it looks like where we would have a horizontal tangent line, and it's a stationary point, and it's going to be a place where x prime of 6 is also most likely 0 as well. So I'll bet we'll find that. I don't want to make an assumption, maybe that isn't the exact location of the local max and min, so just to be sure, I'm going to plug in these times into the velocity function. It's 3/4 t squared minus 6t plus 9. Alright, so plug in a 0 here, and we get 9. So 0, 9 is a point of interest. I'm going to go back to my y equals in my calculator, plug in the formula. I'm doing 3/4. I'm just plugging in this formula. T squared minus 6t plus 9. It's a parabola that looks like that. If we go to the table, we can see that it goes through 0, 9, and 1 goes with 3.75. 2 goes with 0. 3 goes with negative 2.25. Alright, let's try to plot all these. Alright, so that's the graph I get. This is the velocity function. As I suspected, when we trace the local max down at a time of t equals 2, we see that at the same time that we have a local max for our position function, we have that the velocity of 2 is 0. And at the same time that we have a local min, at t equals 6, we also have that the velocity at 6 is 0. Yeah, anytime you have a local max or local min or even a stationary point where it could go up to a plateau and then go like this, that's another place where the derivative would be 0. Alright, our last task here is to find the acceleration function. And in physics, acceleration is going to be the second derivative of the position versus time graph, or it's sometimes referred to as the derivative of the velocity graph. So a of t is going to be the derivative of v of t, which is sometimes referred to as the second derivative of the position function. That means a second derivative. All right, so a of t then is going to be the derivative of 3/4 t squared minus 6t plus 9. Once again, the constant can just be brought down here. And then I'm going to do the derivative on the t squared part. So that's going to become 2t. The -6 can be brought down. And now I'll do the derivative on the t part. The derivative of just a t is 1. And then the derivative of a constant number will be just 0. So our acceleration function is linear. It's going to be 6/4 t minus 6, which is simplifying to 3/2 t minus 6. Now, not surprisingly, when we have a local min for our velocity, that corresponds to the acceleration being 0.